Okay, so Professor Wang, thank you very much for accepting our invitation to have this interview.
It's a pleasure. It's good to talk to you online.
Great. So now let's start. So in the year 2007 and 2010, you proposed the piezoelectric electronics and the piezoelectric optoelectronics devices based on the third generation semiconductor. And last year, you introduced the relevant research progress in Science Bulletin. Could you briefly introduce the current research progress of your team and its future development prospect?
The introduction of Piezotronics was a result of invention of nanogenerator. The first paper on nanogenerator was published in 2006. At that time, I looked at the principle of nanogenerator. I realized there could be a potential generated inside piezoelectric semiconductor materials, crystals. This potential could serve as a gate voltage for transistor. So you know the semiconductor have the voltage which is always applied, but can we use the voltage self-generated by mechanical strain? So that time my research was fully focused on the zinc oxide. So I use zinc oxide as an example. So I proposed the Piezotronic effect. And by 2009, 2010, we applied photon excitation in the system. So we proposed the three-way coupling between the piezoelectric, semiconductor, and photon excitation. So we call Piezo-Phototronics. And these two fields fast involves. And by now, these two effects are the most popular effect for third generation semiconductor. So what are the third generation semiconductor? Like a gallium nitride, zinc oxide, silicon carbide. Those are called the third generation semiconductor. The first generation semiconductor is silicon, germanium, and it has a cubic atomic structure. The second generation is gallium arsenide. It also has a cubic structure, but the piezoelectric effect is very small. The third generation have a hexagonal structure. So crystallographically, they are different family. Okay, so the first generation, second is still cubic. So cubic you have X, Y, Z symmetric. But for third generation, it's hexagonal. What means hexagonal is that in the plane have a 6-fold symmetry. On this direction, only one mirror symmetry. That's it. So therefore, they are not identical. So in the X direction, Y direction is different from the Z direction. So it's different. So X, Y, Z are not identical. It has a piezoelectric effect. So how can we use this effect to change the carrier transport, combination, and separation process in third generation semiconductor? So the Piezotronics and Piezophotonics are about this. Today, we use many third generation semiconductor for power electronics, like silicon carbide, for LED lighting, like gallium nitride. We can use Piezotronic effect to tune the efficiency of those materials, devices. So therefore, as the field advances, it becomes a universal effect for the third generation semiconductor, and also make it distinct from the first and second generation. So now they have a broad impact on photodetector for the sensor-related electronics, as well as LED and the solar cells. So all these are related to this discovery. So I see the broad aspect about this, introduce these two new physics effects.
That's really great. I look forward.
Yeah, and more important, it can also be expanded to 2D materials, like a molybdenum disulfide. It has piezoelectric effect. If the layer is 1 layer and a 3 layer, if more than 5 layers, no more. So therefore, when you have truly thin 2D materials, this effect become important for electronics. So I believe if in the future we write device physics book, they should write this one in book.
Great. It's wonderful. And as you studied under Professor John Maxwell Collin, the pioneer of high-resolution electron microscopy, when you studied for your PhD in the physics department of Arizona State University, so how has this experience influenced you?
Yeah. When I get to Arizona State University, I was just an undergraduate graduate. And I had no idea what I'm going to be. I had no idea what was my interest. Looks like I was interested in everything. So if you're interested in everything, that means you're interested in nothing. So I did not have a focus of my future research direction. I do have a strong drive to do science and also a strong drive to be successful, but I don't know how to be successful. So my supervisor, Professor Collin, was a pioneer of high-resolution microscopy. So when I was under his supervision, I meet many international visitors. That time, Arizona State University has one of the national center on electron microscopy. So they host visitors. And they take Arizona State, this center, as a holy place for electron microscopists. So through that, I know a number of people through that. And at the same time, I said, wow, how come my advisor become famous and everybody come to learn from him, from his lab? Can I do this when I become a mature scientist? So my scientific ambition become higher and higher.
Yes.
At the same time, my confidence built up because before that time, I didn't have any research experience at all. So when I started the research, I found I was not too bad because that time they just told us, oh, Chinese students can only take exam. They cannot do well on the research. Research depends on creativity, depends on the experimental skills. You guys only know how to solve this math and physics questions. That's about it. But I found I was not too bad to do experiment. I was not even reasonably good on do theoretical work too. And so my confidence built up. More importantly, I learned from Professor Collin to love science. And that time he was 60, close to 70 years old, 65, close to 70 years old. Every Sunday, he come to the lab to do experiment. He was 70 years old or close. And I would look for him because he was busy. So I could not find him to discuss my questions. But Sunday morning, he come to lab. So I called him. I said, Professor Collin, I have this question. And he told me this. So please do not bother me this time because I want to use this time to do some experiment myself. Can you imagine a well-established professor by age close to 70 still do experiment himself?
Yeah.
Which struck me a lot. So for today, young people, they get to the university, become associate professor, 35-ish. They say, oh, student, do experiment, report me the data. If you don't come to the first line researcher, you don't know what the creativity is.
Yes.
You don't know the new discovery is because you didn't witness how it was created. So therefore, I learned from him, I must be on the first line of research as long as I can, as in-depth as I can. So that one benefited a lot for my future research. So I learned from him how to be to do science, how to be stay on the first side of research, which is very, very important.
Yes. And you are the first Chinese scientist to win the Nobel Prize in the field of energy, the ENI Award, and the Albert Einstein World Award of Science. What do you think these two heavyweight professional honors mean to you?
I was lucky to be awarded 2 awards, the Annie Award and Albert Einstein Award in Science. Those 2 awards gave to me was recognize me and my team, my people. Over the years, we developed the nanogenerator-based solar power system, blue energy area, especially for the invention of triboelectric nanogenerator, which opened a door for many fields, for many future applications. You can see the broad impact from Internet of Things, sensor network, to wearable electronics, medical care, environmental monitoring, and to also to even pollution treatment, to large-scale blue energy harvest from ocean wave. Those ones, so many people interested. Those 2 awards give to me. First one, it is a recognition to my work by the worldwide. The second one, I have been at least 10 years ago, more than 10 years, 2007, 2008. I was questioned by some people. They say, "Oh, don't believe our data." So after years, shows we were correct. Well received by the worldwide. So it's a recognition to me. It's a reconfirm my reputation, and also same time it is well received worldwide. So I think to me the meaning is a lot. More importantly, it's to the field.
Yes.
This nano energy field. People always say nano energy, little energy. What's the use of that? And if they don't come to see what we do, they're always from the meaning of the terms. Well, what is this used for? This is a machine, nanogen is a machine. But if they should look at that, they find a broad impact for that. So it's a recognition to the field and to the future. So I think I'm very grateful for the committee. They gave me the award, but it's recognition to our team.
Great. Okay, congratulations again. And also, as you founded and served as the editor-in-chief of Nano Energy, now a top energy journal whose impact factor rose from 10.2 in the year 2014 to 16.6 in the year 2020. Would you please share with us your experience in the establishment of the journal?
This back to almost exactly 10 years ago, 2011 this time. I was invited by Elsevier to start a new journal. And at first I say no, because I don't know if I do be a successful journal, because the competition, you worry about the impact factor, you need to devote time for that. But I had a good idea. I tell the managing editor, I say, I may or may not be the chief editor, but I do have a suggestion for you. I have the name for the journal. It's called Nano Energy.
I see.
So she took my suggestion. Next day, she registered the name called Nano Energy.
Oh.
And then she asked me, give me 2 to 3 months to think if I could be serve the chief editor. So okay, I'll think about that. So later I decided to take the job. That was how the journal started 10 years ago. So after these 10 years, I think the journal published many papers. It's not only just the impact factor, it's a broad coverage, number one. Number two, last year published more than 1,000 papers. So we are not just exclusive look for impact factor by limiting the numbers. We only publish 50 papers a year. Of course, just review papers, the impact factor be high. But my purpose is to use this journal to serve the community overbroad.
Yes.
Overbroad, open mind. As long as great science, we welcome. So after this 10 years, I see the nano energy become a broadly recognized field. Same time, the journal grows well. More importantly, we have a platform to serve the large community of authors and readers. So which I'm happy about.
Yeah, that's great. than to serve the community. Yeah, it is the main purpose for the journal. And you were the first to propose the nanometer energy and the self-driven system technology. Also the first to create a friction power theory and applications. Then you are leading the third generation of semiconductor nanomaterials research and transmission microscope in the in situ measurement techniques. So what are the tasks that make you so successful?
I think I can summarize a few things. Number one, we started based on nano is a system. Number one system is based nano energy based high entropy energy system. Two fields is nano generator based solar power system, micro energy and blue energy field. The other one is Piezotronics and Piezo-Phototronics for the semiconductor, third generation semiconductor. So these are the two fields we have done. The third one, we start a few topics. For example, like Piezotronics, Piezo-Phototronics, and Troubltronics. And we also summarize, we have invented 6 new effects by my surprise. Let me tell you what they are. First one is Piezotronic effect. Second one is Piezo-Phototronic effect. Third one is the Piezo-Photonic effect. The fourth one is trouble-voltaic effect. The fifth one is pyro-Piezo-Phototronic effect. And the last one is alternating current, AC current photovoltaic effect. So this one I summarized, and also I will summarize my contribution, summary myself to science. I came out with 7 points. Let me read that to you. So number one is expands the Maxwell equations for the theory of a troubleshoot nano generator.
Great.
Second one is unify the theory for contact electrification, which is a problem for 2,600 years old scientific questions. So the third one, it was develop an interatomic electron transition model for gas, liquid, and solid multi-phase contact electrification. So this, which is a universal mechanism. So those ones we have done. The fourth one is liquid and solid contact electrification and formation new model for the electric double layer, which was done recently. And the fifth one is photon excitation or photon scattering or thermal diffuse scattering in the dynamic theory of electron diffraction image. This is what I done when I was from graduate students to 1996. So spent about more than 13 years on that.
Yes.
So number 6 is the nano balance and the first proposal of nanomechanics inside the transmission electron microscopy. Lastly, invention of zinc oxide nanobelts and the zinc oxide nano systems. So this was the few things that came to my mind.
Wow.
So why I'm very much interested in this one. First one, I love science. I take it as my life. As my job was doing that. Number one. So I'm a scientist. Everywhere I go, I'm a scientist. Okay. Number 2 is curiosity. I love to be new things. New things. Number 3, I like to be distinctive. If I do these things, how can I be different from others? How can I have my own creativity or position or seats in the field, so that we have some scientific invention that will be hopefully future be able to go on textbook.
And my next question is that based on your own experience over the years, how do you think research work can become a top academic and a scientist? When you went through this process, what changes have taken place in your understanding of scientific research and your way of working? As I already said that I take my life is science. I love science.
So you love what you do, and your life is science. So don't take it as, oh, I work only 8 hours a day. If I beyond that, I'm take my own time. We work from the first minute of get up to go bed. Those are the working time. We love what we do. At the same time, we love to interact with graduate students, teach them, tell them my own experience, so they can be more successful. They can build beyond you. Okay, so this is so to be. I think the number one is have creative idea. Always try to have a creative idea. Your idea wins you. Number one. Number two, do not follow the major trend of hot topic, so-called hot topic. If some topic is hot, it'll be cooled down very quickly.
Yes.
Look for the area which nobody cares at the moment. Nobody knows how far you can go. Those are the area have some creativity, and then you start from there. Something invisible, something people think is useless, something people do not pay enough attention to. Then you make your own creativity from there. So this you have to be positive, persistent, and hardworking. A lot of hardworking, because everything you present, you have to use data speak for you. So same time, so everything based on data. Data speak for you.
Yes.
Give you one example. Like this electric double layer, people traditionally believe is only ion sorption on surface. I propose to have electron transfer on the surfaces between liquid and solid. Now I show all the evidence. I show them all the evidence, data here, and so slowly people get what do I mean. So therefore, based on data, and when you get this problem for that, you need to stay focused. Today's we have many opportunity. Young people has many opportunity. They divide their interest to this, and this, and this, and this. Hard to stay focused. If you don't stay focused, you only have limited time. Even you are very talented, but talents plus hard working will make you successful.
Yes. Yeah. Totally agree.
If you don't have the talents, you don't have the wisdom to do things. You need to have wisdom plus hard working to get it through. So this is number one. Number two, stay focused, persistent. Do one thing for 10 years. Do one thing for 20 years, right? Like some of the work, we stayed there for 10 years. Finally, we got it done. Okay, so this sounds not a short time. More importantly, you have the physical picture, vision. Before you do this one, always have a vision. This should be, the mechanism should be this. That's what I think. So have a good math, physics mind is very, very important. Very important. So this is my own experience for that. How can be do things differently? How can you create your own way? Create your way. So all the problem, look from a new angle, is called creativity.
Yeah. Have you ever met any difficulty when you instructing students? So how did you solve this kind of problem?
I have supervised close to 300 PhD students, postdoc, visiting scientists, and some very small fraction of them are this master degree students. So most are PhDs. Most of my students doing very well, excellent. Also have the students who do not willing to work hard, who do not do that. We do have those one students for that.
Yeah.
So I always talk to them very kindly. Number one, tell how important what you do now. And you work for yourself, it's not for me.
Yes.
You write one more paper, one less paper, it doesn't matter to me. But for you, it's critical important.
Yes.
So you work for you, not for me. Number two. Number three, if you do well on the graduate study, you can find a great job.
Yes.
Right? You're gonna higher salary, have a great future. I'll be very happy for you. I'll be very happy for you. So I want to be yourself motivated. Same time, you be successful. then your success is my success.
Yeah.
If I can help you to get your success, I'll be more than happy to do so. So I tell those to students and mentor them nicely, at the same time, hope them to be listen to me. And if they still cannot do well, I'll ask some other senior students to help them, guide them, work together. You two people work together. So get them through, and after they graduate, if they continue, I'll help them. If they go on their own way, I'll give them best wishes. If they say, well, goodbye, so all right, have all the best futures. That's about it.
You are a wonderful supervisor. So how do you manage your research team? I know you have a very big team.
I have normally the team is relatively large. I think when I was the Georgia Tech, my large team was we have 47 people. Today, when I'm in Beijing, my team has 44 people. Still not that big, but we have many other PIs. I need to supervise them too. So you need to divide into groups. Okay, each group have 1 to 2 topics.
Okay.
Each team has 2 to 3 people. Normally 3 people. Is a postdoctor, senior PhD student, and a junior student. They are one teach the other one, so you have a continuation. Okay, so subgroups, number 1. Number 2, different topic on different ones. They write to me the reports once every 2 weeks. Write me use PPT, write a report to me, so I read them and I discuss with them if I need to, and if the writing cannot help the communication, I use the face-to-face meeting. So all this will help me to communicate with them, make sure that they get the idea and proceed well. I think this way to work with students and a group. Also, we have group meetings. Okay, choose students give talks. You give talks, and we have questions ask you. Number 1 is report your vision. Number 2, training, oral presentation.
Okay. And do you have any hobbies? And how do you balance your work and family?
I do. I love sports. I like to do exercises. Okay, and I like to have meetings with other people, have a drink or have a dinner or something. I do. I do. As a good scientist, not only just work on science. It's also communicate with people. If you do well, tell other people what you've discovered is what your discovery can impact the world. So it's a good communication skill. It's very, very important for that. And of course, that you work a lot. You do that. You sacrifice a lot of family time too. Okay.
Yeah.
So they see how to be a successful scientist. They can follow.
And do you have any influence on your children's choice of major and career?
I found I was some success, but not always. Let me tell you that my suggestion is show your kids what you do. Bring them to the lab, take a look, and share your excitement with them. Share how happy with your research. At the very beginning, I remember when this many years ago, I took my 2 daughters to my lab. When we do nanomaterial synthesis, they look, oh my God, dark, dirty. This tube has this nanomaterial that we don't want to do that. Well, that's just when they were young. They don't know what you do. But when they grow up for that, they start to be interested in that. I start being interested in that. And just like my second daughter, and she graduated from material science. And one of the topics she did was on nanogenerator. For that, she watched for you. And so I think let them choose themselves.
Yes.
Let them follow their own interest. Interest is the best teacher.
Yeah. Yes.
Is the best. If they interest this one, they will do persistently, consistently. You don't have to tell them. It's up to them to do what they love to do, and they'll be very successful. Encourage them, say, follow your interest. Just go. As long as you're successful, as long as you're happy, I'm happy too.
Okay. So, Professor Wang, thank you very much for accepting our invitation to have this interview.
It's a pleasure. It's good to talk to you online.
Great. So now let's start. So in the year 2007 and 2010, you proposed the piezoelectric electronics and the piezoelectric optoelectronics devices based on the third generation semiconductor. And last year, you introduced the relevant research progress in Science Bulletin. Could you briefly introduce the current research progress of your team and its future development prospect?
The introduction.
Time. Mm-hmm.
Okay, please.
Well, welcome to this week's special ICANX lecture, our 52nd week. I'm Paul Weiss from UCLA and also the editor of ACS Nano. And it's my very great pleasure to host today on behalf of Professor Alice Zhang and Professor Jagadish. Our honor today is to bring back Professor Zhonglin Wang, who's a world-leading material scientist and engineer. This is his second ICANX lecture. Last year, his first set a record with over 600,000 attendees. At Georgia Tech, he holds the Hightower Chair in Material Science and Engineering and is a Regents Professor. He founded and leads the Beijing Institute of Nanoenergy and Nanosystems. He invented piezoelectric nanogenerators, discovered and applied Piezotronics and Piezo-Phototronics. Many of the foundational papers, I'm proud to say, were published in ACS Nano, where he's published more papers than any other author. He's a foreign member of the Chinese Academy of Sciences and Academia Sinica. He's won the Albert Einstein World Award of Science, the MRS Medal, and many other honors. He's the founding editor of Nanoenergy. He's also a great friend and a terrific representative of our field. And it's my pleasure now to turn over the floor to Professor Zhonglin Wang.
Okay, let me move this one. Let me share the screen first. Okay, just a second. Share screen. First, I'd like to thank Paul for the great introduction, and I'd like to thank Alice, Paul, and all the colleagues for organizing this wonderful lecture series, which impact the world science in a broad way. And in this special time, in this difficult time, what they have done is for nothing but advanced science technology worldwide and make us stay in contact, and science belongs to the humankind. Thank them for the great effort. I think today I'll have the great pleasure to talk about one of the area I've been working for last 15 years or so. It is called Piezotronics and Piezo-Phototronics of third generation semiconductor. So when you hear this title, it maybe sounds strange for those terminologies, but I will explain to you what do they mean. Okay, so let me start with this my lecture. In my last 20 years to now, I mainly do two things. Number one was nanogenerator based solar power system and blue energy. The second one is Piezotronics and Piezo-Phototronics based on third generation semiconductor for advanced devices. So in the first lecture, I was mainly focused on this nanogenerator. Oops. On today's lecture, I focus on the right-hand side of this tree, which is on the Piezotronics. Let me explain to you what it is and what it can be impact our optoelectronics in a broader way. So in the last 10 years, the world move on. What happens belong to beyond Moore's law. We know one day the Moore's law will reach the limit. Is that the end of the world? The answer is no. Beside the speed, we look into functionality. We look at more things which can be integrated with our daily life. For example, wearable electronics, personal electronics, soft materials, and self-powering technology. So the world is moving beside the speed, but also on the functionality, which is called a smart world, smart city. Okay, so that's what we are looking at. So when we offer this functionality, let's look at what the semiconductor can do. Let's look at the first generation semiconductor, which is a silicon-based. The second generation is a gallium arsenide-based. For silicon and germanium-based one, which have a so-called diamond structure. So it's cubic structure. So the X, Y, and Z are symmetric. For the second generation, is also cubic, but it's diatomic. Okay, 2 atoms made of this lattice. So it has some of a small piezoelectric property if on the mechanical strain, but it's very small. So once you move to third generation semiconductor, things change gigantically due to the crystallographic structure from cubic to hexagonal. So what's the difference? Hexagonal means that in this axis we have 122 degree free-fall symmetry. On this direction we have only mirror symmetry, which is gigantic different from what we had in first generation semiconductor. So therefore, on the mechanical strain, the piezoelectricity of third generation semiconductor is there, is unavoidable. So that's why we talk about the impact of piezoelectricity on the transport in the third generation semiconductor. That's why we start this work back 2007, 2010 or so. Okay, so then you say, what for the third generation semiconductor? What are the applications? Gallium nitride based radio frequency devices, silicon carbide, gallium nitride power electronics, and gallium nitride based solid state lighting. So we use a lot of solid state lighting now for display and lighting. Those are as of now, the major application of the third generation semiconductor. So how can we tune their optoelectronic performances? So that's what I'd like to talk to you today. Okay, so when did we start this work? Again, this is back to the work we did in 2005 for the nano generator. At that time, we say, oh, we have a vertical nanowire with an EFM tip triggered, and we see a small voltage output. This later on to give the birth of nano generators. So when I give the first talk on ICANX, I talk about nano generator. But today, I talk about if you have a piezoelectric semiconductor, if you have a piezo potential across it, what this potential can do for tuning the transport of carriers through this semiconductor? Can this potential serve as a gating voltage for the semiconductor? So we talk about the piezo potential to piezotronics, which is what I like to talk about today. Okay, so this gives you a brief idea when it was started back in 2005. Okay, what is nano generator? Nano generators utilize piezoelectric property of zinc oxide. Zinc oxide is a material which have this is a hexagonal structure, Wuzat structure, but the cations and anions are tetrahedrally coordinated. So the cations and anions does not have a central symmetry. So on the mechanical strain, cations and anions polarize, give you a small dipole moment. So if each unit give you a small dipole moment, the whole unit give you a macroscopic, measurable piezo potential, and this piezo potential can drive the electron to flow back and forth if you apply the mechanical strain periodically. So this is what we call the nano generator, because converter cycled mechanical action into electric power. So the answer is very simple for that. But now let's make a change. Instead of apply a load, we apply something different. Instead of apply a load, When we do this one, we have a buffer layer. So this layer prevents the carrier to flow through the interface, through the semiconductor, reach the end. So now, if you get rid of this buffer layer, instead of apply a load, you apply a voltage. And this voltage can drive the carrier to go through the system. So this is the carrier transport. But now, if you have a piezoelectric polar charger at the interface, can this serve as a gating voltage for control the carrier transport through the entire system? So that's the question. Can a piezoelectric charge serve as a gating voltage for the charge tuning, manipulation, and control? So the answer is yes. So this is the basic principle of Piezotronics. Use piezoelectric create interface charge to control carrier transport across the entire system, which is this is the basic idea. So when we first phrased this one was 2007. So I wrote a 3-page article saying, oh, we call this nano Piezotronics. Why do we call nano? At that time, we used nano wire for that. But today, you don't have to use nano. Use thin film, use bulk crystals, you still have Piezotronics. So we just call Piezotronics is a new effect and field. Okay, so what it is? Let's look at if you have a Piezotronic transistor with the C-axis perpendicular nanowire. We have a semiconductor which is piezoelectric. Who are these materials like a zinc oxide, gallium nitride, silicon carbide, those materials? Okay. Now, if you have a 2-terminal device, if you apply a mechanical tensile strain, what you do is create an internal potential. This potential can be a couple of volts. So therefore, as a result, you have a depletion zone. Some of the carrier segregate towards one end due to the potential drop across nanowire. As a result, the channel width reduces. You can control the charge transport. So this is the principle, which can be utilized as a gating voltage for transistor. So if you can control the carrier transport, you can build a transistor. Okay. So the traditional way, what we did was that use a gating voltage to control the charge carrier flow through the source to drain in the semiconductor. This is FET. Now, this external voltage is being replaced by internal voltage, which is different. We only have 2 terminals, which have the functionality of the 3 terminal. So that's the difference. So the first case is CX perpendicular to the nanowire. In such a case, you can calculate the potential, you can calculate the depletion to the charge carrier, etc. All this can be simulated by existing softwares. Okay. Now, let's say we have a gallium nitride nanowire. The CX could be upward or downward. It doesn't matter. For the carrier through the system through here, you can measure the nano device, the transport on the compressor strain and the tensile strain. You can see the transport current is almost symmetric on the compressor strain and the tensile strain. So this is the device. So we can tune the transport through such, because it doesn't matter you have compressor strain or tensile strain, the tuning to the whole device is different. This is because the CX is perpendicular to nanowire. But now let's have a case if the CX is parallel to nanowire. If this is the case, the polar surface for this will be right at the interface. If you have a n-type semiconductor and a metal contact, you have a Schottky contact. The tensile strain induced, compressor strain induced negative ion raise the Schottky barrier higher. If you have a tensile strain, you have positive ion will lower the barrier height. So the barrier height at the junction here can be raised or lowered. Remember, this is the barrier height. It can dramatically turn this device on and off because the tuning is exponential. It's not linear, exponential. So you can turn the device on and off. So this was for the case such we work on for the CX parallel to nanowire. So let's do the experiment. The experiment is such: if you have a free nanowire, no strain, we have two ends bonded. You measure the transport across this wire, you get this dot curve, which is this. Now, if you on the tensile strain, you apply a bending to the substrate. The nanowire be on the tensile strain. You're gonna see the red curve. That means it's a diode. This is on, this is off. However, if you bend the other way, is nanowire on the compressor strain, you can see the green curve. This is on, this is off. You can see the difference between green curve and red curve from the dark curve, black curve, is just one half. This is the interface tuning. Why is this? If you have an interface like that, metal contact, both ends can have short contact. If you apply a compressor strain, this have negative polar charge, they have positive polar charge. What does the negative charge is raise the barrier height. This is lower the barrier height. So raise barrier height prevent electron flow this way, but does not affect electron flow that way. But this lower barrier helps the electron to transport this way. So this is open in this way, but not that way. Now, if you change the compressor strain to tensile strain, this side is negative charge, this is positive charge. Negative charge raise the barrier height here, lower the barrier height here. So electron cannot flow this way, but can flow from the other way. So this tuning is opposite to this tuning. So you can see this. Two are in contrast. That's called the interface tuning. Asymmetric tuning is due to the different sign of polar charge at the two ends. This was the very first paper we published in 2008, and we proposed the mechanism of Piezotronics, and through the last decade work, it further extended our understanding about this mechanism. Okay, can you convert this into theory? So say, okay, we can do this one, use the simple semi-classical theory. If we have a PN junction, this is the voltage part. You can see if the voltage is positive, this is amplification, the current goes through. So this is the voltage control. Besides the voltage control, in front, there's a piezoelectric control. You can see this is exponential of a positive number except the charge density. So if the charge density is positive, this let the current to flow through. If the polar charge is negative, it cuts it off. So this is exponential piezoelectric control. This is the voltage control. One can control the other one. Okay, so you can see from a simple theory, it shows use piezoelectric control, you can turn this device on and off, which is similar to the role of gating voltage. That's why we call this a transistor. A transistor is nothing but use the gate voltage to control the transport of carriers from source to drain. So that's in compared to what we know. Of course, if you can calculate numerically, you know that this is we already know about that. So this is the PN junction. Okay. So now, if you have a case for the vertical nanowire, because chemistry is very amazing, you can grow nanowires vertically or laterally. You have a catalyst at the end. Normally for cadmium cell nanowire, the CX is parallel to the nanowire. So if you apply AFM tip to this, you measure the transport across this as a function of the force you apply. We found that if you have a 420 nanonewton applied, the turn-on voltage is half volt. But once you have a 700 nanonewton applied, the turn-on voltage is 1.5 volts. Why is so? Because you apply a different load. You create different density of voltage at the interface. You control the carrier transport distinctly different. So this is called mechanical strain, create a polar charge, control the transport of the device. So this is for the vertical nanowire. So if you make a one vertical nanowire, which is not dramatic, can you make array? The answer is yes. So if you have a source of drain, you have a gate. This is the FET design. Now you get rid of the gate voltage. So you have a single nanowire here. This is internal voltage replace external voltage. You have a source and drain. You can have this device like this. So if you can make one with this one, you can make an array, a crossbar electrode like that. So between this, you have nanowire. You can apply mechanical strain individually from pixel to pixel. We'll be able to make the first chip for Piezotronics. And this, you can inside here, if you cut through it, inside you have the parallel piezoelectric nanowires. You can make this array of device like that. So what it can do, you'll be able to apply the mechanical strain individually from pixel to pixel, so you can control the transport from pixel to pixel. This is called a Piezotronic transistor arrays. Each 1 centimeter, we have 8,000 such of transistors. There's not very many yet, but it was the world first Piezotronic transistor arrays we'll be able to fabricate. So this is the Piezotronics I'd like to introduce. Okay. Now, can you? Sorry, this is a little fast. Can you do this? I'm sorry about this. If you have a metal semiconductor metal contact, zinc oxide have a polar direction. If this surface is zinc terminated, this surface will oxygen terminated. They are different polarity. So now, if you have calculated short barrier height at the two ends, you found that if one end on the compressor strain for the zinc terminated surface, with the increase of strain, its shock barrier change from positive to negative. On the contrast, on the oxygen terminated surface, its shock barrier height increases. This opposite change is the distinctive characteristic for distinguish piezotronic effect from piezoresistant effect. So it's a nonlinear rectification behavior. It is asymmetric. It's asymmetric tuning. It's have a strong polarity. It's an interface effect. This is a distinct difference characteristic from piezo-resistant effect. You can use experimentally. You can change the size of strain. You can change the strain, the voltage applied. You'll be able to distinguish if this is a piezotronic effect or piezo-resistant effect. That's the theoretical first principle calculation for that. So now, if you can do that, you have a flexible substrate. You can put one piezotronic transistor on top, one bottom. You'll be able to build a logic circuit. You'll be able to use strain to control logic computation. In the past, we always do logic computation with voltage control. This use strain to control the logic computation, utilize piezotronic effect is a new way to do it. So we did this work. We want to show it can function as what we used to do for logic control. Okay, so this is the first path. I talk about piezotronics. Now it's Piezo-Phototronics. So what is this? Piezo-Phototronics is we apply photonic excitation beside piezoelectric and electronic transport. So let's look at this. If you have a p-n junction, one side you have piezoelectric effect, the other side does not. Let's say the n-type has piezoelectric effect. So you have a charge depletion zone, which is charge depletion zone. If you on the tensile strain, the negative ion change the tuning a little bit here. This on the compressor strain, you'll be able to reverse the sign of the polar charge at the interface. which can change the band structure of here slightly. This slight change not only change the band structure, but also shift the pressure zone right or left, depending on the sign of the polar charge. So the question, can we utilize this effect to control the charge recombination for LED or charge separation for solar cell? The answer is yes, we can utilize to do that. So let's show you the tuning. First case is LED. For LED, we'll be able to find a P-type gallium nitride or N-type gallium nitride wire. We put one on top. You apply a mechanical strain stress like this. So once you apply, the stress remains rigid, static. You don't have to do cycle, just rigid. Then the light emitting is strongly affected by the strain applied. Why so? Let's do the experimental measurement. See, the intensity of light emission depends on the strain introduced in nanowires. Okay, so we found with the increase of strain, the lighting intensity can enhance by a factor of 3 to 4. Some people may ask, is this a contact problem? The answer is no. We do all the measures to ensure this is an internal effect. You can measure as the strain increase, the yield intensity increases gigantically. So why is so? The reasons as follows. So if you have a P and N type junction here, you have an interface. The interface, let's say N-type piezoelectric effect, the polar charge is 1 or 2 atomic layer thin. In such a case, you introduce a small dip here. This small dip is nothing but to trap the electron a little longer so it can go pass by. If you can trap the electron a little longer, it increases the electron hole recombination rate because the mobility of electron is higher than hole. So it is the electron mobility determine the emission intensity. So if you hold the electron a little longer, it gives you more light. That's what we see. If you apply mechanical strain, you see the lighting intensity enhances. So this is what we know for sure. Okay. Now, beside this, theoretically, we all found that not only this little trap existence, that's what we found through numerical calculation, but also the depletion zone can shift to right hand side or left hand side, depends on the sign of the strain you apply. So if you have a depletion zone, you can shift the depletion zone right hand side or left side, which is very, very important for tune the carrier transport at the junction. So in such case, you do that. You can tune such. Okay. So I'd like to tell you what is happening. Making one device is not dramatic, but you can make a 22,000 LED array. Each nanowire at the root is a nano LED. Can you individually control the strain at the root so its emission light intensity will be changed? We can do that because each pixel we can independently control that. So therefore, after you apply 0.15% compressor strain, all these 5 letters can give you very distinctive LED emitting light. One nanowire is 1 pixel. This is something very important. Show you we can make an array of devices. This Piezo Phototronic device array. So we not only make one, we'll be able to make an array of that. So this shows the Piezo Phototronic effect proposed. This effect is universal, not only for gallium nitride, it's also for zinc oxide and gallium nitride. Zinc oxide and a polymer, p-type polymer. Zinc oxide and a p-type silicon, zinc and quantum dots, all are. So it's universal. It's a truly physical effect. And more important is room temperature effect. So you can apply a room temperature to tune a transport. What happens if you use this effect to tune the heterogeneous heterojunctions of electron gas at aluminum gallium nitride, and gallium nitride interface? These are practically very useful quantum well and quantum dots. Can we do that? Let me show you. If you have a quantum well, due to the lattice mismatch between aluminum gallium nitride and aluminum nitride, there's inevitably strain at the interface, no doubt. So as a result, the band structure bending downward. So there's a free electron gas being trapped at the interface. This Hampton device is very important for power electronics. The density of this is important for its performance. But due to the intrinsic strain, once this device is made, you cannot change this density per your wish. Once it's done, it is done. That's it. So now, can we apply an external mechanical strain who can tune this artificially? Can we do that? So the answer is yes. So therefore, if I have a positive piezo charge here, positive piezo charge lower the band a little bit, so the more free electron trapped on the interface here. We increase it. If you have a negative ion, which raise the barrier, the band a little bit, less electron being transported. Can you do this linear? The answer is yes, we could do that. So experimentally, we make a device which we can linearly control the strain. We found the density of free electron gas at the interface can be linearly tuned by strain. You can, per your wish, tune from 10 to the 16th to 20 to the 21st by a few factors, almost factor 2 or so, linearly through that. This is a tunability we can do. So once you do that, you'll be able to enhance the performance, make it better. So this is for quantum well. What about quantum dots? Due to lattice mismatch, you can see lattice constant for gallium nitride is 3.189 angstrom. Indium gallium nitride is 3.263 angstrom. This is the lattice mismatch. So when you make quantum dots, the internal strain, the internal strain present is unavoidable. So if you have an internal strain, the band will be tilted. So with the band tilted, the electron will be accumulated at this end, the hole will be accumulated at this end. They are misaligned. The maximum electron hole recombination is this when they align. If they are misaligned, well, the recombination rate is reduced. So how can we make an electron and hole wave function maximum overlap? So we apply external strain to overcome the tilting of the band, so you can maximize the two transition from electron to holes. So we can do that. We found when we apply a mechanical strain, we do show that the lifetime of the carrier reduces. That means the carrier cannot survive too long. Where the carrier go? Recombination. So the LD emission intensity enhances. So you can do this one. You can say, oh, we can tune the carrier lifetime or tune the carrier recombination rate. We can do that. So this is the first example, show you LD tuning. The second one is solar cell. Solar cell is the opposite to LED, is the electron hole separation. Okay, so there's many cases. You can do this for perovskite solar cell. You can do this for general semiconductor-based solar cell, but we do for silicon. The reason because we believe silicon is one which have already commercialized for large-scale application. So we grow zinc oxide nanowire, which is transparent, so the light can go through it. Then we find what? We can tune the performance, this homemade solar cell by Piezotronic effect. So you can do that. If you have a piezoelectric charge create interface, you can change the carrier separation recombination rate gigantic. If you have a device at a zero strain, the absolute efficiency is 8.8%. Okay, that's the absolute photon conversion efficiency. Now, if you apply a compressor strain, it becomes 9.4. From 8.8 to 9.4, we got almost 0.8, 10% increase in solar cell efficiency. Is due to the phototronic effect. And this case, we do the very many cases here. I just show you one, we can do that. So this is the photosolar cell. The other case is a photodetector. Photodetector is also solar cells use photovoltaic effect. So if you have a silicon cadmium sulfide, this near infrared sensor, we found if you lights on and lights off, you apply zero, no strain apply, you almost get a zero response. But if you have 0.15% compressor applied, you find the responsivity increased by 3 to 4 orders of magnitude. It's called gigantic increase. Now, what about the response speed of the photodetector? After you apply the strain here, the response time increased by 3 to 4 times, which is very important, or 6 times. So it means response faster and better. Why is so? Is because of phototronic effect for the carrier separation. And we have many examples for this for photodetector. Since you improve kind of 3 to 4 order of magnitude. What about this array of devices? So there's many ways you can make nanowires. One way is growth. The other one is etching. So you can use an array of etchings. You can create a letter C. You use this to enhance the UV photodetector by this. And we found it was gigantic enhancement in the photo response as you apply mechanical strain across. See, okay, this is the light intensity, and this is the mechanical strain here. You can increase almost 10 times so. Okay, so this is one example. The other example is that you can make this one pixel from pixel. You make a high resolution mapping of the distribution across the board. So the reason I show you this briefly is that for photodetector, solar cell, the same principle use of piezo phototronic effect to enhance performance. The fourth case is sensors. Okay, we know people make sensors. They make a nanowire very small, very thin. They say why? Because we want to have the surface gas molecule absorption, so we can change the depletion zone gigantically. So fabrication becomes very difficult. A few years ago, we found that's not the best way. The best way is shorter contact. If you have a shorter contact, you have a one charge species absorbed on the contact. You can tune the barrier height significantly, which is gigantic, tune the transport of carrier through this interface. So this is the short contact for sensors. So utilize this, we show the enhancement of photo sensors, gas sensors, biosensors, and many different sensors. You can see our review, which companies can give you why this is better. So do not use omni contact, use shorter contact. And then we have biosensors. Utilize this effect, we can enhance the sensitivity by a factor of 5 or 6, which is large for in the solution. So we found this is universal, so we can have photodetector, chemical detector, the biological detector, we can do the enhancement. So this use the piezo phototronic for such. What about catalysis? People talk about the photocatalysis. People talk about electric catalysis. Can we enhance this with piezoelectric effect? So we have one example to show you. We have many papers published this one. So you have a barium titanium particle. On surface, you have silver oxide particles. So you put in the sonic wave, the sonic applied, and BTU has a polarization. Let's say at a special moment, this end have the negative piezo charge. This end have positive piezo charge. Now, positive piezo charge attract the electron across to the surface, to the interface, reject the hole to the surface. So this is hole rich. Here is negative ion attract the holes, reject electron. So this is electron rich, this is hole rich. Redox reaction. Experiment found that by using this one can largely enhance the degradation rate of organic pollution. It's called piezocatalysis. It's not a photocatalysis, it's not an electrocatalysis, but the use of piezoelectric effect enhanced catalysis effect. And you can look at this review paper, will give you a good idea what we're doing by here. Okay. Lastly, spin transport. For people doing spintronics, they always look at low temperature. We show you at room temperature, we can do spin control as well. Okay, the system we look at is zinc oxide is P3HT, this kind of hot junction. When you do spin transport, you have a number of ways. You can change the symmetry of the device, so-called bulk inversion asymmetry. You can do that. This is called the Rashiba term introduced this structural inversion. Okay. From this principal discussion, how do they do it? They started the linear light polarization and circular light polarization. For circular light polarization, the dependence is on a 2 phi, which is the incident angle of the polar light. For the linear light is 4 phi. So you measure the effect of two different frequency. You can distinguish this is circular polarization or linear polarization, because circular polarization relate to spin up and spin down. The difference between spin up and spin down, this give you the term. So we measure, let's say, okay, we have a strain, we have the tensile strain 0.8%, we have negative 0.8 compressive strain. You measure the photocurrent depends on incident angle, change from a periodical function to something which is not simply a periodic function. You can simulate this one by two functions. Use the so-called circular polarization function. And the green curve is linear polarization curve. You get a final fit. From here, you know how much percentage is circular polarization, how much percentage is linear polarization, and you plot them as a function of strain plot. You find on a compressor strain, it has more circular polarization. Once you tensile strain, it has less. So you can use the strain to tune the spin up versus spin down. So in other words, room temperature Piezotronic effect tune the strain spins. Why is so? Let's give you a simple explanation. Let's say you have zinc oxide and P3HT band diagram. So you have this spin up and spin down. So now if you apply a strain, this is the positive ion here, which is lower the band furthermore, which separate the two bands more here. The separate two term more give you what? A large difference between spin up and spin down. That's why at such case you see the enhanced circular polarization light emission here. Okay. Now if you reverse the strain, you have a negative ion here, which raise the band a little bit, which make it too close. So the difference between up spin and down spin get less. You get this case. So the reason I show this one, you can use this Piezotronic effect to tune the spin orbital coupling in your devices here. Next one, I'd like to talk to you about the Piezotronic effect in 2D materials. 2D materials is very active research field, very excellent property, very good to do. Now, if I have a single layer molybdenum disulfide. It is lacking of central symmetry. For bulk molybdenum disulfide, it has no piezoelectric effect, but it has a single layer, double layer. Double layer means what? It have a projection central symmetry. So there's no piezoelectric effect. Can we measure this? So the answer is yes. So a few years ago, we make a device that can utilize the Raman spectroscopy to identify we have monolayer, double layer, triple layer. Experiment we find, we make a nano generator here. So we apply mechanical strain, we can measure the carrier flow through the system. So measure the current. We find for single layer, triple layer, 5 layers, we have piezoelectric output. But for double layer, 4 layer, 6 layer and above, no such effect. It shows 2D materials can have a piezoelectric effect only for older layer of atomic structures. This provides another degree of tunability. In addition to photonic electronics in the 2D material, you can expand that. And this, can 2D material have piezotronic effect? The answer is yes. If you have piezoelectric effect, you must have this. So you have a single layer. You measure the transport from positive bias to negative bias. You found that the transport property is this. If you apply 0.71% strain, you find the current increases on the positive bias, but on reverse bias, it reduces. This is called reverse change. Why? Is because the polar charge at two ends are reversed. This is piezotronic effect. This is called piezotronic effect. However, if a double layer, you find if you raise the strain on the positive bias, the current increases. On the reverse bias, the current also increases. So both increases, which is called piezo-resistant effect, which does not depend on the direction of the polarization is, give you this piezo. So you can distinguish what is piezotronic effect, what is piezo-resistant effect through experimental measurements. Okay. Next question: how thin the sample can be? You still have piezotronic effect. So we made a 2 nanometer thick slab. It doesn't matter how thin. 2 nanometers should have 3 units. If the top is zinc terminated, the bottom will be oxygen terminated. This polarity, even you have 1 unit cell, you preserve. So you have piezotronic effect because on the mechanical strain applied, the current increases, and here current drops. This asymmetric change give you the piezotronic transport. So in other words, you can make a phototronic device as thin as 2 nanometer. It still functions because the polar charge is 1 atomic layer. That's it. That's very localized, very distinctive from conventional just external voltage control. This is interface polar charge controlled. So what's new here? I talked a lot about this. What's new here? New is that you have semiconductor photoexcitation. The integration tool is optoelectronic, huge area. What are the material we utilize? We utilize gallium nitride, aluminum gallium nitride, silicon carbide for those devices. For the people who work on a piezoelectric, they rarely utilize gallium nitride for piezoelectricity because the piezo coefficient is much lower than the PZT. So the material they utilize is PZT. PZT is a good piezoelectric material, but is not a good piezoelectric semiconductor. It's an insulator. So now if you use 1 compound semiconductor, like a gallium nitride, you burn them together, you have the piezotronics and piezophototronics, which are new area. So what we have is 1 layer of polar charge at the interface. You change the carrier separation or recombination. You change the depletion zone, move right hand side or left hand side, depending on strain you apply. This gigantic change the optoelectronic processes. So we name this as a new effect. Total 3 new effects. The first one, use the polar charge to tune the carrier transport at the interface junction. You make a new electronics called Piezotronic effect. Use the piezoelectric polar charge to tune or control the charge separation or recombination at the interface. You call Piezo-Phototronic effect. Lastly, use piezoelectric, you can induce photon emission, which is a new effect, which is talk about this. Does this exist? The answer is yes. So we observe the experiment. Let me show you. What I like to emphasize is that these are all room temperature effect. You do not have to cool down to millikelvin or Kelvin. Room temperature, it functions. What I personally believe, what are the most useful effects are room temperature effect or higher temperature effects. Because if you need a lower temperature function, in reality, it's very hard to use. How much energy do you have to consume to keep a low temperature so low? You're going to take a long time to bring that work temperature to room temperature. It's a long way to go. So what I like the room temperature effect, we can utilize immediately. So for zinc sulfide nanoparticles, when the zinc sulfide is bulk, it have a zinc blend structure. But when the zinc side is small, it have Wuzha structure. On the mechanical strain, it give you light. No voltage applied, but when you apply mechanical strain, it give you light automatically. We also find the light intensity increase linearly with the pressure applied. Why is so? This is the pressure-induced photon emission. Just apply mechanical strain, it has photon emission. The higher the pressure, the more the photon emission. What a simple explanation. Zinc sulfide have a 3.7 electron volt band gap. On the mechanical strain, its band structure being tilted, so you have polar charge at 2 ends. The surface state have trapped electrons. So when the band is tilted enough, the trapped electron will come out. This trapped electron will jump to the lower state, release energy which is above the energy of band gap, 3 electron volt above. Because zinc sulfide is doped with magnesium, this energy could be excite electron transition from the A1 state to T1 state in doping. And then it jumps back, give you photon emission, which is the orange color you observe experimentally. So this is a piezo effect induced photon emission. In the whole process, we have no voltage, no external voltage, no current applied, but it gives a photon emission due to this possibly piezophotonic effect, which has been demonstrated for that. Okay, you utilize this effect, you'll be able to do the signature. You can record the force pressure applied for the signature for this, right? So this effect not only for nanowires, but also for thin film. Even for p-type materials, we made the thin film. We observe the piezotronic effect in a similar way, because we make a piezoelectric film with the piece axis downward or upward, depends which way you change the last terminal layer on the substrate. You can do that. This paper gives you all the details. We measure that piezotronic effect also applies to p-type materials, which is different from the n-type materials. So make this effect more generalized, more universal. If you have this effect, it doesn't matter A-type, N-type, P-type, you have it. Okay. Now, for P-type, many people question zinc oxide. Can you make a P-type zinc oxide? Some people say yes, some people say no. What are our answers through our research? The answer is yes, you can make zinc oxide P-type. And some people say how stable they are. I would say at least within 1 year or so after sample being made, this was still stable. I cannot guarantee this is going to stay for 10 years or so. So we can make P-type zinc oxide with antimonide doping. From such a doping, we be able to observe, we can prove that the antimonide doping network is P-type through the transport, which is the standard transport measurement. We can find piezo-phototronic effect. Piezotronic still preserves for P-type nanowire. So it doesn't matter if you are thin film, P-type or N-type, as long as you are piezoelectric semiconductor, you have this effect. So therefore, it's a new physics effect. You don't have to call nano. Why call nano? We first case call nano because we use nanowire purposes, but now this is more general, generic effect, universal. You can observe for many systems for that. Okay. So I'd like to add a few things more to this one because Paul is the chair of today's session. I'd like to give my gratitude to Paul. The first paper on Piezo-Phototronics was published in ACS Nano in 2010. The second paper was also published in ACS Nano because we submit to other journals. They said, well, what is this? Never heard about this one. Must be wrong. Reject. Thanks, Paul, for publishing those papers. This is 2010, 11, 12 years ago. It's turned out to be a big physics effect. So, in many cases, a new concept come does not mean it will be appreciated by the science or nature or the referees or editors. May not be, but you should get it published one way or the other through a dozen years effort to show this is the case. It works for many cases here. So I bet those papers are cited reasonably well. So we should be thanks to ACS Nano for publishing those papers at early days for that. Lastly, I want to emphasize to tell you flexoelectronic effect in cubic systems. You know, when I talk piezotronic effect, we talk about hexagonal structure, which is asymmetric of the crystal, give you the polarization. But now, if you have a cubic lattice on a mechanical, non-uniform mechanical strain, you can create crystal lattice distortion. Can this give you localized piezotronic effect? Over thickness integrates flexoelectronic effect. The answer is yes. You can use an AFM tip to induce non-uniform strain, measure the transport. You can find this is the flexoelectronic effect for that. But I personally believe piezotronic effect is much stronger than the flexoelectronic effect. It has, to my own opinion, much broader application and flexoelectronic effect. Even some people study for that. But because you say why? You see, flexoelectronic effect is an integration of many localized, segmented piezotronic effect. It's like the relationship between flexoelectronics and the piezotronic is integral and differentiation. Many functions can have a different differentiation, but when integrated, it has the same results. So therefore, it's very hard to claim something is purely due to flexoelectronic effect. It's going to be difficult. You also have a piezo-resistive effect about that. That's why make this effect good to study, but for practical application, you got to be very careful. Is this truly integrated result of many other effects for that? Okay, so I'll just bring for to show you we did prove in cubic system due to change of symmetry we can produce flash electronic effect for research purposes. So at the end, I'll show you three-way coupling between semiconductor, photonic excitation, and piezoelectric. We have a field of Piezotronics and Piezo-Phototronics, which in the last decade so we demonstrate many ways of tuning for LED lighting, for flex electronics, for photo detector, for spin, for LED display, many things. You can name it. Today, especially people look at micro LED. When you get LED to micro scale, there's a gigantic strain at the interface. How can you optimize the performance of micro LED? Use this effect. It will be very interesting to study for it. So you can do the tunability for that. So in the over years, the field grows slowly but surely. So we'll be able to publish this in the Piezotronic transistor in science, Phototronic effect in nature. So all this one get a wide range of acceptance. Okay. So I mean, what is the concept once is proved will be accepted by the community, but slowly, surely. I bet if we publish the first paper in Nature Science, it will cause a wow effect. People say, wow, wonderful, this will be much terrific. Okay, but through a dozen years, we show step by step. Eventually, we receive much more solid, much more confident results at the end. This was almost 2.5 years ago. M.R.S. Bulletin published a special issue, have 8 papers summarize the worldwide effort in the Piezotronics and Piezo-Phototronics. So this become 2 new effects, 2 new field for 3rd generation semiconductor. So once we move to device physics for 3rd generation semiconductor, I believe they need to write those effects in the chapters. They cannot. There's no way they can avoid it. There's no way they can minimize that. It is there. They have to utilize to enhance the performance of devices. Okay, so when anything from beginning, people say, what's the application for this one? Say, oh, this may not be useful. Well, it could be. Who knows? Look at the first transistor. Look at the first integral circuit. If you were in 1948, 1958, do you believe those would be useful? Probably yes, probably not. But today, nobody doubts. So be open-minded. Anything at the very beginning is crude. It's not very looks nice or beautiful. Only after decades of thousands, millions of people's work make it perfect, make it useful now. So, but the originality is there. Can we tolerate such from 0 to 1 research? Can we give them time to grow? Many cases, people say, wow, this can have no application. They don't believe this can be useful. How do you know it will not be useful? How do you know it will be useful? So I think give time, support basic research, support this. It will show in one day, in some way, maybe in the future, will shock you in one way. Okay, so I'd like to thank many of my people from Georgia Tech team, from Beijing Institute. Over the years, these people work with me persistently on this topic, and many collaborate. They contribute that to the work today. So summarize, today I mainly introduce Piezotronic effect and Piezotronic, which as a new effect, a field for 3rd generation semiconductor. Also Piezo-Phototronic effect, which give you tuning to optoelectronic device. And lastly, I give you the one to the Piezo-Photonic emission for that. So those ones, I introduce a new effect, but more important, room temperature effect. It is because it is function at room temperature. But of course, if you lower to lower temperature, it works much better too. But it still works at room temperature. Then I believe it will be very useful. It will be very useful in our future device, in our daily life, whenever you find a good niche point for it. Let's keep looking. Let's keep working. I believe one day we're going to find something. This is important discovery of effect, which can make something better than we thought. People may think you can apply strain cycling. No. Strain cycling is only for energy generation. For this effect, you only find a rigid strain, fixture it, then it will function. I think this one can be make it easier for engineering. Its response frequency can reach to megahertz because the piezo polar charge have a response speed of picosecond, nanosecond. So we should be able megahertz range should be a good one. So I believe it can be utilized in that frequency range. But of course, we need more people to study for that. Okay. So with that, I'd like to thank the Paul for kindly chair this session. I'd like to thank Alice for kindly invite me for the second time so I can give you this talk. And then I'll be more than happy to answer your questions. Thank you.
Terrific. Thank you so much. Yeah, I think I will take over the screen here.
Okay. Very good.
Yes.
Okay.
Well,
Okay.
fantastic. That was just, another amazing lecture. And we had actually several hundred comments during the lecture, from which we've chosen 4 questions. So the first is, are there limits that you see for nanofabrication for devices, given the chemical and materials complexity here?
Okay, very good question. We did a 2 nanometer thick. This device was trying to see what's the physical limit. We found because the thinnest we could make was 2 nanometer. So we found it works. I personally believe even when we can make a 1 unit cell, which is 6 angstrom, it should work as well. So I see the limit is probably 1 unit cell. That's what I say. But if you thin the net, there's no such a need. But if you can 1 unit cell like 6 angstrom, which is very small enough for many purposes for that. So I believe the limitation could be 1 unit cell. That's what I might answer to this question. And of course, that's the thickness. And laterally, you can make the smaller size PIO. You can use lithography method for that. So I think in a 3-dimension X, Z, you can make a truly very tiny Piezotronic transistor. So I see that all the possibilities. It could be complex because there's involved this material, the manipulation, strain application. But we're looking for some functionality. We cannot compete with current electronics for speed, but we can challenge them with them for functionality.
Very good. Our second question is from Yin CG at Waseda University. Thank you for your impressive talks. I read your books on triboelectric nanogenerators. Although this is not my research field, I'm very interested in it. My question is, what is the future of TANGs? Can you share some of your ideas on promising research directions and commercial opportunities?
Yeah, thank you. This is the, I gave a talk in the first IconX lecture on this topic. Mm-hmm. And Tang is the area of my majority of effort. This is utilized diverse choice materials. Triboelectric effect is very universal. Any material have this effect. So we can utilize for sensors, for power generation, and for many applications. Especially today, we're looking for Internet of Things, sensor network, big data, this artificial intelligence. Everything needs data. So where the data come from? Come from photo detector, imaging, from motion sensors, from mechanical tricking, from anything you can sense give data, they can do that. TNG is a powerful technique provide the data. It also a powerful technique to provide the related small power you need for such data. It also can be utilized for even larger scale energy, for blue energy for that. And recently, we use TNG as a probe for study liquid and solid interface, which I have not talked about that today, maybe in the future. So it's have a broad impact. And at least I will tell you, I will devote my next 20 years in my lifetime on this research and its possible technology application. I will not do anything else but focus on these two areas, the TNG and the Piezotronics.
Terrific. Our next question is from Xiaobo Li at Xidian University. What are the future goals of the piezoelectric field, and will it lead to practical applications? What's the biggest challenge in achieving these goals?
The piezoelectric is a field that is well established. It always has new frontier in that field. It already has many applications. So if you don't know the piezoelectric application, there's many textbooks you can read, a review article for that. So what we do is, in addition to piezoelectric effect, we add additional effect. So I think can add more new and exciting application, which we may not know by now, but I think fundamental research is exciting because we are explore unknown.
Let's see, and our fourth question is from Guandi He at Northwestern Polytechnical University. The voltage generated by piezoelectric nanogenerators is generally low. What do you think are the possible pathways to magnify the voltage?
If you remain on the piezoelectric materials, the voltage is normally low. Why? Because you have a crystal. You want to, the voltage you generate depends the magnitude that you can compress the crystal. So if you have a crystal, the scale can change very small. So that's why the voltage is low. This is the reason back to 10 years ago, we discovered the triboelectric nanogenerator. We have a large deviation in amplitude, so we have much larger voltage output. More importantly, we have much more expanded material system. Please look at our TNG work, and then I think you will be better idea what you should do, how to magnify the voltage you are looking for.
Terrific. Thank you so much. As I said, there are several hundred more questions, but what I want to do now is welcome our panelists.
Okay.
So, and we'll keep you here for discussion. So,
okay.
First, we have Dr. Sang-Woo Kim, who's a distinguished professor at Sungkyunkwan University and director of the BK21 for SKKU Materials Science and Engineering program, where he's also head of the graduate program in the department. He's an associate editor at Nano Energy, ZL's journal. He has won the Research Award of the National Academy of Engineering of Korea, the Korean President's Award for Scientific Excellence, and many other honors. Then we have Dr. Zhonglin Wang, who's at the University of Chicago, where he's an assistant professor in the Pritzker School of Molecular Engineering. He's won an ONR Young Investigator Award and been a Technology Review 35 under 35. He did his PhD with ZL and a postdoc with another ICANX lecturer, Jinan Bao, before starting his independent career. And our ex-challenger today is Dr. Wei Huang, who's a research assistant professor in the chemistry department at Northwestern University. He's a leading researcher in next generation electronics, and I believe that he's quarantining in Shanghai and coming to us from there. And I'm delighted to welcome our host, Professor Alice Zhang from Beida, to join the panel as well. So welcome, everybody. And as is our tradition, we'll start with our ex-challenger, Dr. Huang.
Oh, great. Hi, Professor Wang. It's so amazing to see that piezo Piezotronics has so many applications in so many various areas. So my first question is that I've seen your presentation that the highest strain of these devices can endure is to be around 1 to 2%. And so what is the high strain it can in fact endure? And is it possible to extend the application to like wearable electronics where as high as 30% of strain is needed?
Yeah, a very good question. You know, for crystal, you normally apply, I would say less, even theoretical say they can apply a couple percent before the crystal breaks. The experiment finds about 0.5%, even less than device we face. If you have a device like say you have 30% strain, which is way too large for crystal, But what you could do is that make a device small, segmented, so you can only experience local strain change. You can have a device over such a length, you have a 30% strain, but in the region here, you can be just a small expansion in the length, which could be possible for such a case. So that in that case, if we can find new material system, let's say, can we find a organic piezoelectric semiconductor? In that case, we could extend the extendability of the device. So if we could find such a material, I think the strain scale can much more extended.
Okay, thank you for your answer. It's very inspiration. And my second question is that it's about TNG. So the power output of TNG is similar to that of an AC source, which would need external circuits like capacitors to maintain consistent power output. So consequently, this might further increase the complexity and decrease the mechanical stability. Since there are also flexible like lithium ion batteries. So when compared with these other energy source strategies, what is the advantage of TNG?
Oh, good question. Let me first one show you. We don't want to look for a system. Let's say, okay, energy harvesting, management, and storage. So we have a system we call a self-charged power unit. Such system can be used sustainable. If you put an environment, you don't need to be recharged for that. If you have a battery, you have to replace once in a while. Okay, so compared to the current existing technology like a battery, capacitor, supercapacitor ones, for power density, the TNG may not as high as that, but it can make the battery sustainably continuous working. So the number one advantage. Number two, TNG is not only a power source, but a sensor. So anything you trigger it, give you a signal. Anything trigger it, say, for example, if you put the TNG in my throat, when I talk to you in a seminar, due to the vibration of my throat, this radio frequency generated from here, wirelessly in 10 meters away, be received. There is no amplification, anything needed. Such a sensor cannot be afforded by other devices. And this is the second advantage. The third advantage is that it is a high voltage source. We can use TNG as generator plasmas. We use TNG for electrostatic motors, which needs high voltage. We can do that with this. So not only just compare from an energy density, energy generation storage point of view, but also from other things the battery and the supercapacitor cannot do. Then you can understand why it has so many superiority.
Thank you. So my last question is that, can you share with us some, like how was the idea of the Piezotronics originally conceived? And maybe a little bit of history on that?
Yeah, this was back to 2006. We published the first paper on the nanogenerate. In the paper, there's totally 4 figures. Number the number 3 figures was the mechanism proposed. Why use the AFM tip trigger single nanowire give you a voltage output? Why this the direction of the voltage is such? So I try to explain that use a diagram. Now I draw is a piezo potential distribution across the nanowire for that. After the paper published, I was wonder how large is this potential, because we was just proposed the idea, proposed the mechanism. We did not do the numerical calculation. So one of my students do the numerical calculation. Find it can be for a 50 nanometer nanowire. It could be as high as 0.8 volt, which is very large, because you have a 50 nanometer wire apply a half a volt across nanowire, which is large. So and then I said, well, if we apply this, we have an internal half voltage. Can this be a gating voltage for that? So we started thinking this one. Then said, well, we don't have any evidence for that. The critical evidence we provide was that we made a zinc oxide nanowire. For example, let me use a pencil. Okay, this is a zinc nanowire. We use the AFM tip to push it, bend the nanowire, and then we measure the transport. As the degree of bending increase, we found from an ohmic contact become a diode. That's what we found back to 2006. How come a mechanical strain make the transport behavior change from ohmic to Schottky? Must be a barrier created interface. What barrier? Could be piezoelectric charge create barrier. So that was my first impression for that. Just a second. First impression. Don't worry about that. It was my hotel room there, the telephone code. Okay. This came here, and then I said, well, there's a barrier here. Later on, say we proposed the Piezotronic idea. I came out the idea back to 2006, December of 2006. Also, I gave a talk in the MRS conference. I had an invited talk about the nano generator. Then I changed the title. I changed the title to Piezotronics. So I talk about the idea. This is December 4th, 3rd, 2006 fall MRS conference. After that, there was a reporter from Chemical Engineering News. He comes to, hey, Dr. Wang, tell me, what do you mean by Piezotronics? And she asked me, what do I mean? So I explained to her what I was thinking, and she wrote a half-page report afterward. That was the first report on this idea. So that was a very vague idea back to that time, but I was be able to speak out on that. So that's how it was first created. Later on, we move on more today.
Great.
Thank you.
Simple idea, just a straightforward feeling.
I think Huang was, we saw all these things because that time you are already a student there, right?
Yeah, I'm really fortunate to be the witness during those very exciting years of the birth and the progress of all of those Piezotronics, Phototronics. Yeah, I still remember the time. Professor Wang just talked about those papers published in ACS Nano.
Paul, let me tell you a trick. You probably never noticed. I never tell you about this. When I wrote the first paper on the Piezo Phototronics, I was really worried the referee could reject this one. I said, what this thing is. So I wrote the article, and at the very end of the article, I wrote one sentence. This device called Piezo Phototronic device. Mm-hmm. And somehow the referee did not pick that. Get it published.
I do remember that.
Get published. Then in the second paper, I placed it in the title. Mm-hmm. Also it says Nano.
Mm-hmm.
Very, very good. Yeah. Mm-hmm. Okay.
Well, I think let's move to Professor Zhonglin Wang. Here's your chance. What would you like to ask?
Yeah, so it's really great to see, how much progress this field have made just during the past 10 years. So it will be great if Professor Wang can discuss more about like what could be the things happening to this field in the next 10 years. So I bet probably like everyone, maybe besides Professor Wang, cannot really imagine like if we date back to 2009, 2010 of how much progress can happen just within 10 years time. It's not a long time.
Yeah, definitely. Sehong and I experienced all this together. And let's say back to 10 years ago, 2011, TNG was just, this is March, this is April, May. That time we just have some data. I was working with Feng Ru, say, is this an artifact or not? I was trying to prove that with him by that time. But today TNG become a big field right now. And the same thing for the Piezo Phototronics that time we just proposed. But today people slowly realize, accept this effect. Then what are niche applications? So that's why I give this talk to the people who work on the semiconductor field. I give a talk to people in the IEEE field. I hope they say, oh, this can be applied for this immediately area for that. So we are still looking for niche areas they can utilize for some specific purpose. So we are still looking, and hopefully everybody help us look to speed up the application. I have no doubt about the TNG application of Piezotronics. Going to take some in-depth thinking to find something truly unique.
Very good. And let's move to Professor Sang-Woo Kim, who I believe was a visitor at Georgia Tech as well.
Yeah, thanks, Professor Wise. Okay, Zhonglin, excellent talk. So I really enjoyed your talk. So so many people around the world are actively doing the nanogenerator research. So they're definitely, so it's thanks to your excellent global leadership. I'm very grateful. So actually, I have watched it for a long time. So you have worked hard and done your best to make our community the great and huge. But still, I always curious. So what is the driving force to dedicate yourself to the research?
Yeah, sounds good question.
Yeah. Thank you.
Like the reasons that we as a scientist, we have limited capability, we have limited time and resources. But what is unlimited is our love to science. I enjoy what we do. I love what we do, and devote every time I have to the research, because that's how I believe the things I can do the best. If the other things I may not be anything close. So dedication is important. More importantly, in-depth thinking. Same time, persistency, because curiosity and persistency keep me going. So the reason, so you ask me this question, I would say, I love what we do. That's the things I can do the best. Then I try to do the best in this regard, and that's why we can move from one step to the next one continually for the years.
Yeah, thank you. The wonderful answer.
Yeah.
And Alice.
Hi, yeah, I do have many questions.
Right.
Yeah, actually, I see a lot of students was ask questions here. So one most important question is to Zhonglin Wang. So how you manage your time? Looks like you're sleepless.
No. That's not. I need to sleep 6 to 7 hours a day, because
really, so it looks like you work all the time.
No, if I cannot sleep well, I cannot work well. The most important is dedication and efficiency. Some people just do things in serial connection, one after the other. I always do things in parallel. So I can do 10 different things at the same time. I can treat 10 different things at the same time. So I try to be in parallel process. So just like Paul is working very efficiently, he has multiple windows open and doing that. everybody have 24 hours. You need eating and sleeping and interact with people and enjoy normal life. At the same time, how can you do more than other people? Is that try to be efficient. If you can do this today, don't wait tomorrow.
Oh, that's the best words. Yeah, so if I can finish it today, just finish.
I love it. Alice, I'll tell you this famous quotation from a professor told me years ago. He said to me, if you have 5 minutes, do 5-minute thing, number one. Number two, do not read the same piece of paper or do not read the same email twice. Once you read it, deal with it. Then you save time. And if you have a window, you have all the icon here, everything over here. You don't know what you're doing. Keep your desktop clear so you know what your focus is. You know what I need to do today. Then you improve your efficiency for that.
That's great. We learned that.
I have a related question, and that is, how has this year been different? Normally, you were flying back and forth between Atlanta and Beijing, every other week and using a lot of airplane time to edit, I think. But that's been so difficult. How has your life changed and how have you adjusted in terms of, what you've done and been able to do, or maybe found a way to do more?
This is the reason that what I miss the most this year is to be able to miss the opportunity to travel and meet many colleagues like you. And in normal time, we meet a couple times a year and spend some time together. I miss those a lot because like you, we have many colleagues, collaborate friends. We cannot meet, only can through this online meeting. And also the other ones that we tend to sit too much too. Then gain some weight too.
We're also working on that.
Yeah. So we need to work hard. Well, I need to work hard myself at least.
Oh,
yeah, really, everyone missing each other. Yeah, in the very beginning, we see that we need meet face to face.
So I think the most important is that this online talk at least keep us in personal contact. Also keep scientific exchange across the globe. We still believe science need exchange. Science need communication. Science belongs to humankind.
Yeah, thank you very much. Actually, Paul, you know that last year we started this talk exactly as what Zhonglin said. The reason, we want to, keep moving, let everyone know that science is still active and everyone will still, can collaborate even online. Yeah, we are family.
Yes. Yeah, we'll certainly work to see how we can continue this once the world reopens.
Yes, that's right. We look forward to that. Yeah, really love those days. Really miss those days.
Yes. Well, thank you all so much. Let me move on to what we would normally do: walk across the stage and present a plaque to Zhonglin. But we'll
send me the electronic one, right?
Here's your second virtual one, and we'll look forward very soon to being able to see you in person and to talk more about the future of science in the field and everything else going on with our students and families. In the meantime, please accept this virtual certificate and the promise that we'll have a chance to see each other.
Let me take a picture of this.
In person soon. Oh, we will send it to you too.
I take electronic myself. Yeah, even we do not meet in person, I wish my friend, wish you all well. Stay safe and happy, and let's hope we can meet soon.
Absolutely, yes. And next week at ICANX, we'll have Nader and Gaeta from the University of Pennsylvania, hosted by Jagadish, and again, a terrific panel ahead. And coming up in the next month, we have a Nobel laureate, Jean-Marie Lane, Pulika Lajayan, Stephanie Lacour, and JiaBin Huang for June. So, please do continue to tune in each week. And thank you again to Alice and her team for organizing and hosting these wonderful lectures. And thank you again to ZL for an amazing hour and a half with us.
Yeah. Thanks very much. Yeah. Thank you.